Cool. So, hi everyone. My name is Gabel. Don't worry about pronouncing it, because you probably won't. I work for a medium-sized company in Israel called Wix, and that's on the Nascent subject. Instead, what we're going to be talking about is DSL design in Scala. So, the way this talk is constructed is basically a quick overview about what DSLs are and what they're aiming to do. And then I'm going to walk you through one possible flow for kind of attacking this issue of how to design a DSL in Scala. I'm going to give an overview of a few techniques and tips and tricks that you can employ if you're going that route. And hopefully, by the end of the talk, you'll have a better idea of how to get started and hopefully how to get a lot of things done, and at least a few pointers about things you can research and play with all that as you're designing your DSL. So if there are any questions at any point, please feel free to interrupt me. And let's get started. So, DSLs, domain-specific languages. For obvious reasons, they're designed for specific application domains. Okay, you have an application problem, you have a domain that you want to tackle. Some domains include things like testing, querying. There's a whole bunch of options, but the context of any domain-specific language is to solve a specific problem in a way that makes it much easier for your users to operate in that domain as opposed to using a general-purpose language. The big deal about domain-specific languages is that because it's limited domain, and because the solution space is small, okay, you're designing small languages, not general purpose, you can make a lot of assumptions that enable you to optimize the syntax for things like conciseness, okay, having the code be small. If any of you have been to George, aka Fuloma's talk about Prolog yesterday, you saw the difference between having a bit of code in Prolog and having it in Scala. Okay, so Prolog can be considered in a sense a domain-specific language for logic programming, and you can get the same stuff done with the Scala type system, but it takes a lot more code. So that's conciseness. Obviously, correctness is desirable, readability. Okay, the idea is to let your users operate within that domain in a way that's natural, simple, efficient, effective. DSLs come in two flavors. External DSLs, which we're not going to be talking about beyond a quick introduction to what they are languages that are standalone, that are external. They have their own specification, their own grammar, and they require very explicit support from libraries and tools in order to work with them. So for instance, one example of that would be SQL. Okay, SQL or SQL for data querying on top of relational databases. That's a domain-specific language, and it has no context outside. It has no use outside of the context of working with a relational database. One other thing to note about external DSLs is that the life cycle for code written in those languages is also very explicit. Okay, this thing does not get evaluated, does not get parsed. Nothing is done with it until you feed it into a database, at which point the database engine parses it and generates an execution plan, etc., etc. Another example is Markdown. If you want to do text formatting, for instance, if you're using GitHub, you're liable to be using Markdown, and that's a very simple domain-specific language for text formatting. And that's everything we're going to be talking about for external DSLs, because they're not that interesting in the context of Scala. What is interesting are internal DSLs. Okay, so an internal DSL is by definition a language that's hosted within another programming language. So any library that you have that you use in Scala, such as ScalaTest or Specs² that gives you a DSL, that DSL, that domain-specific language, lives in the context of a host language. And it means several things. First of which, why even bother? The idea is to extend the host language to support a more readable, more concise, more correct syntax for a specific domain. The idea is to add syntactic constructs that enable users to work within that domain more efficiently. And one curious thing about it is that the code that your users end up writing in your internal domain-specific language is by definition valid, in our case, Scala code. Okay, you can't make up new syntax, you can't make up symbols, you can't change the semantics of the host language. Another interesting aspect of it is that the life cycle for any code written in a domain-specific language is by definition tied to the life cycle of the host language. Okay, if you write tests within a ScalaTest spec or rather a Specs² specification, the life cycle for that code is tied to every other bit of code you have within that compilation unit. Okay, it's not something that you need to explicitly parse or invoke or do anything with. Examples include, as we discussed, ScalaTest. Okay, this is just a bit of test code, and it extends the Scala language to offer you syntax such as should, okay, or this validator left thing. Don't worry about what it actually does because it's not that interesting. But what is interesting is that this validator left should be a success. This is not, not out of the box Scala syntax. It's extended syntax that's provided to you by the library that you're using. Other examples could include routing. Okay, declaring routes in Scalata or Play or Squeryl. That's also typically a DSL in of itself. And another example is generating in-memory JSON syntax trees with, in this case, Play JSON. Okay, so this is just a very, very quick overview of what DSLs are. I expect, are there any questions at this point? No, okay, terrific. So, yeah.
You could also have strings, right, with the macro language where you could create strings that generate code, right?
Are you talking about string? So string interpolators. Yes, although I wouldn't consider them to be a domain-specific language. It's more of a syntactic construct that is provided to you out of the box that you can somewhat use to provide nicer syntax. But it's not, it doesn't really allow you to extend the Scala syntax per se. It's debatable. So, before we go on, what I'm going to be doing is I'm going to walk through the process of designing a very simple DSL. The example I chose was data assertions. Okay, you have a piece of data, you want to make some assumptions about what it is, what it does, what's its shape, and then you want to assert on those assumptions. So that's going to be the example, and it's going to be very, very obvious in a few slides. So the first thing you need to do when you design a DSL, any DSL at all, is to know your domain. Okay, you're working in the context of a specific problem. If you don't understand that problem, obviously you're not going to be able to develop a useful domain-specific language for it. So the first, one way of going about it is the first thing you do is you try to be specific about your domain. So you break it down. Okay, what are the actors? You have players in the equation. Okay, so for data assertions, you have the programmer actually making those assertions. That's the actor. You have actions. Okay, an actor by definition takes an action, and that action by definition is acted on some object. So what are your actors? What are the actions they take? What are they acting on? And finally, what are the consequences of those actions? So in the context of data of assertions on data, you have a caller. A caller is basically the programmer that's using your data assertion DSL. The caller has a piece of data that's outside your language. It's coming in from somewhere. And an assumption on what the shape of that data is. And they want to assert that the data they have takes the shape that they assume it takes. And the consequences, for our purposes, of this assertion failing is a runtime exception being thrown. So in this context, we have just one actor. Okay, that's the caller. That's a programmer using your DSL. We have a couple of objects. Right? We have the piece of data, and we have the assumption on the shape of that piece of data. And we have an action. The assertion is an action. Okay, I have a piece of data, I'm assuming something, I assert. And we have a consequence, which is the throwing of runtime exception. So this is what we're starting off with. The second thing you need to take into account are your users, your audience, as it were. Which actors do your users represent? If you have more than one actor, you may have more than one entry point into your DSL, more than one context in which to operate. Also, you need to take into account what is the desired consequence of that action. And most critically, you need to put yourself in the shoes of your users and try to figure out how would your users express this desire that they have. Okay, they're using your language, they have some consequence that they want to see happening. The whole point of a domain-specific language is to make it as easy as possible to express that desire. So in the context of data assertions, we only have one actor, we only have one consequence. There's a reason I chose this as an example, because it's easy. The real question becomes how to best express the user's desire. And if we put ourselves in the user's shoes, I'm a programmer. I have a piece of data. Okay, so the piece of data is the only given thing in any context in which I'm doing assertions on data. And I have some assumptions about the shape of that data. So the first thing we need to tackle is we need to provide the user with a way to declare these assumptions. And the result of that language that we provide the user with needs to be highly readable, needs to be concise, it needs to be usable. The second thing we need to do is to provide some syntax for actually making that assertion. Okay, you have your data, I'm giving you a mechanism to declare assumptions, and I'm giving you a mechanism to assert on these assumptions. And probably the last, or maybe second to last thing you need to do before you actually start modeling your domain-specific language in Scala is you need to pick a vocabulary. Okay, so your actors are either implied or they're part of the language, depending on your domain. Nouns typically describe actors. Okay, you sometimes need to qualify, nouns describe objects. You sometimes need to qualify these objects, so you use adjectives. You have verbs, these are the actions. And then you have adverbs, which are qualifications on these verbs. And I'll show an example of that in a second. So, data assertions. Okay, now we get to the meat of the subject. What is an assertion? An assertion is a sentence. Okay, I have a list. I want to assert that the list is empty. One way of expressing this, and a pretty trivial way to express this, one that's employed in ScalaTest, Specs² and others, is something akin to list should be empty. That's my expression. That's the assertion I make. So I have an object. Okay, list. You probably can't see this. I'll forgo the laser thing. List is an object. And I have an action. Okay, I say list should be. That's my verb. Okay, that's how I invoke my assertion. And then I have a second object, which is my assumption, which in this case is actually an adjective. Okay, because what I'm saying is I have this list, I'm asserting that it should be, and the description I provide is that it's empty. And this is what I'm aiming for. Okay, this is the expression that I'm starting off with as I'm constructing my DSL. In this case, the actor is implied. Okay, it's not part of the sentence because I'm the actor. I'm making the assertion. It's not part of the language in of itself. Other bits of vocabulary for data assertions include things like, what are my assumptions? What assumptions can I make on data? So I can assume that the data is empty. I can assume that it's null, true, false, etc., etc. Some of my assumptions might, take parameters, might be parameterized. So if I'm assuming that, I take in a person, and I'm assuming that the person is an adult, my assumption would say something along the lines of, this person's age should be greater to or equal than 18. I could have assumptions that the data is equal to something, or that a string starts with something, etc., etc. All of these are different assumptions that I can make, and that's part of my vocabulary. Finally, I may have adverbs, which is what I mentioned before. And you can consider these to be modifiers. Okay, so not is an adverb, and it's a modifier. Okay, if I have a list, and I want to make sure that this list does not contain the element 2. Okay, I have this contain, or contains an assumption, and I want to invert it, negate that assumption. So that's a modifier. Okay, so we start off with this. This is a conceptual vocabulary for the language that we're constructing. The last thing we need to pick, and this is a bit of full disclosure, right? This is my observation in my words. It's not based on academic research or anything. But I've observed that DSLs really come in one of two modes. Okay, you have an imperative DSL, which sometimes is called shallow embedding in the context of Haskell and some other languages. This type of DSL eagerly evaluates expressions. Okay, what's returned from expressions in that language are effects. Okay, I don't expect to get back a representation of my expression. I expect that expression to be evaluated and to get back the result of that expression. So examples of that may include data assertions, as we saw before, or it could include things like AND tasks. Right, an AND task, no one uses AND, I hope, but if you happen to use AND or have used AND, okay, there's a domain-specific language built on top of XML, but AND does not care what the structure of your target is. Okay, it reads it in, as long as it's valid XML, it starts running through it. And if it fails, then fine. You know, it just spits out an error and stops. So it evaluates as it deals with as it parses your domain-specific language. The more interesting type of domain-specific language are what I call prescriptive DSLs. Okay? An expression in a prescriptive DSL generates or prescribes a bit of behavior. And that behavior is then handed off to a separate execution engine for whatever action I actually want to take. So one example is a query language. Okay, if I'm using SQL, the fact that I wrote an SQL and fed it into a parser does not necessarily mean that I get back the results from the database. I need to take the prescription that the parser spits out, hand it off to the database for execution, and then I get back the results. So the reason this type of DSL is really powerful is basically that when you get back behavior, you can reason about that behavior. You can, for instance, optimize that behavior. Okay, you can optimize the results. You can, if any of you use scalding or Spark, okay, it may take your queries that you're constructing, your workflows, and optimize them for whatever reason. You can't do that if they're eagerly evaluated because everything happens on the fly. Okay, so that's one aspect of prescriptive DSLs or deep embeddings that makes them more powerful. And finally, they're harder to get right. Okay, you need to have some sort of model for the expressions, for the behavior. You don't just act. Okay, you generate a description of the behavior, and that's what you return to your host, to your caller. And evaluation, obviously, is the other side of the equation where you take in the model and you act on it, and then you actually have your effects. So, the example in question, data assertion, because this is a fairly short talk, is going to be an imperative DSL. Okay? It's going to eagerly evaluate things on the fly because it's easier to demonstrate. But the principles of how to construct a DSL are actually quite similar. It's the results that are different. So, next up, we've covered the basics of what our language should do and what it should look like, at least in the abstract. In order to actually implement such a language in Scala, the second thing I need to know is I need to know Scala. Okay, I need to know the language that I'm going to be hosting my domain-specific language in. And there's a bunch of building blocks in Scala, possibly the most important of which is something called infix or dot-free notation. So what this basically means is that I can take any function application that just takes one parameter, it's called arity1 function application, and I can encode it in the language in Scala with no dots, just with spaces. Okay, so these two things load this object, taking method from an object and invoking it with one parameter can be written in a dot-free syntax just by omitting the dots and the parentheses and adding spaces. The reason this is so critical is with any domain-specific language, typically you don't want to have that cruft. You don't want to have dots and parentheses strewn all over the place. You want to get rid of it. And one of the nice things about Scala is that it allows you to do that with some caveats. So, the things you need to know about infix notation are, well, some of the things anyway you need to know. Chaining is a problem, okay? And by chaining I mean having several expressions one after another. Okay, I have an object, method, parameter, some other method, some other parameter, etc., etc., etc. It's hard to get right in the context of the DSL because if we take a look at the sentence that we had before, we have an object, we have a method, and the assumption is we have a parameter. And reading this in English, you'd assume that bEmpty would be, through some magical process, would be your parameter. This is what you expect, but this is not what happens. Okay, infix notation is very, very literal. Okay, it just takes next token, which in this case would be b, and feeds that as a parameter into your method, which usually is not what you want. Okay, what the behavior will be depends on the type of b of that word. If it's an object, that object gets fed. If it's an implicit conversion, the compiler will throw up its hands and say, you know, I don't know what to do here. I have this thing that I can't apply to anything. So this is probably not really what you meant. So there are two things you can do to work around this. Did I just go back for some reason? Huh, I'm missing a slide here. Apologies. There's two workarounds for this. I'm going to do it freeform. The first thing you can do is you can contract. Okay, you can say list should be. Okay, you just take the b, stick it onto the end of should, and then you have a verb that's just one token. You call your action should be. That's one thing you can do. The other thing you can do is, unfortunately, add parentheses. Okay, you could say list should be, open a set of parentheses, stick the empty in there, and close it, because the compiler knows that b being a function takes a parameter, it evaluates it, and it takes the result as the single parameter to the infix expression. So those are really the only two ways I'm familiar with to work around this limitation. The second thing is you have this expression once again, and you have list should be. So let's assume this is a sensible syntax. The result of this is an object. Empty is a method, but we don't have a parameter. Okay, so what this means in practice for your domain-specific language is that any sentence, any expression in your domain-specific language must have an odd number of participants. And literally, this list should be empty expression is not legal, valid Scala code. You just can't have that type of sentence in an internal DSL in Scala. Actually, there is one workaround for this, and that's to use postfix operators. Don't. Okay, and let's just leave it at that. Oh, the slides got reordered. Love it. Okay, the second building block is implicits, or rather implicit classes, and in some rare cases you might end up using implicit conversions. I'm not going to touch on that. So implicit classes are good for the examples that we're getting here. Implicit classes give you an entry point into your domain-specific language. Okay, so we have this corrected expression, list should be empty. We have a piece of data that's known beforehand. Okay, when your user comes into your DSL, they already have a piece of data in their hand. So that's the list. And then should be is an extension method. Okay, if the piece of data is an integer, obviously it does not have a should be method. Okay, same with sequences or just about anything else. So we need to add that somehow. That's what implicit classes are for. The type you extend, okay, the type of list is domain specific. Okay, in the case of data assertions, we can assert on pretty much any piece of data. That piece of data can take any shape, right? So in our case, the type we extend is some type T. You should prefer value classes for performance sake, if you can help it. If not, depending on your DSL, it may not be an issue. And one other use case for implicit classes, which I'll demonstrate in a bit, is they're also used to lift values back into your DSL domain. I'll show what I mean by that in a few slides. Any questions before I get into the code up until this point? This was sort of an introductory thing. What are the things you need to know in order to actually implement these things? No questions. Okay, moving on. So let's get into the code. As we said before, an assertion is a sentence that takes a certain shape. That shape is some piece of data should be some sort of predicate, okay, or some assumption over the data. The first thing we need to do is we need to define what a predicate is. So in this case, we have a trait. That trait is called predicate. It's contravariant over some type T, because an assumption over some supertype is usually a valid assumption over a subtype as well. For instance, if my assumption is that something is null, that applies to any reference type. There's two things in the predicate to start with. There's the test that takes a value of this type T and returns a boolean, whether or not this assumption is met. And there's a failure string, which returns a failure message in case the assumption is not held. The next thing we need is an entry point into our DSL. And the only thing we know is we know the data. Our user already has the data. So we need some sort of implicit class that gives us the should be verb and adds it into our domain language. So we have an implicit class, which the name doesn't really matter, but it's better to have a meaningful name. In this case, to demonstrate, I just picked entry point. And it only has one method, okay? It operates over some type T, and it takes in a bit of data, and it gives you a should-be verb that takes a predicate. And the implementation is as follows, okay? This is an imperative DSL. A failure has consequences, okay? Has an effect. If an assumption does not hold, we get an exception out of it. So, what the implementation could look like is this. Okay, we take a predicate, we take the test out of that predicate, we apply it to our piece of data. If it fails, we just generate a string based on the failure message, we spit it out. Okay, this is the most trivial implementation I could come up with. Now that we have a piece of data, we have an extension method, and we have the framework for defining predicates, we can actually start doing this. So our first predicate, just to make things interesting, is nil. Nil should be empty. Okay, so our first predicate is emptiness of some type of sequence, or the most general purpose thing I could think of was a gen-traversable once. A generic solution for this is actually pretty easy to implement. We have an empty method that operates over some type T that is a gen-traversable once, and it generates a predicate. The test is simple. We just use the isEmpty method from the gen-traversable once. Our failure message is that the value we get in is not empty. Okay, so this is pretty trivial, and from this point on, things get a little bit more complicated. Not that much more. Booleans. Okay, we mentioned before in our vocabulary, we had some assumptions about things like whether something is true or false. And Booleans, these true or false things, are Boolean literals. They're keywords, reserved keywords in the Scala language. You can't override the semantics. You can't provide a method with that name. You can't provide an object with that name. You can use backticks to kind of give it a literal-like symbol, but then your users will also need to use backticks, and it's horrible. It's not what we want. So there is a workaround to support the syntax, and that ties into what I said before about implicit classes. We can lift Boolean values into predicates. Okay, so the way we do this is we simply add an implicit that takes in a Boolean and gives back a predicate. And the test is simple. We just take in a value, we compare it to the Boolean we got, and if it fails, the failure message is that the value we got is not the value of that Boolean. This gives us the ability to say things like some Boolean expression should be true or should be false. We have a somewhat similar issue with null. Null is also literal, also a keyword, but the annoying thing about null is that we can't lift it into a predicate. Or rather, we can add an implicit, we can lift it into a predicate, but it's not going to work because The signature for should be for our verb takes in a predicate over some type t. That's a reference type. So if you do anything should be null, it always resolves to this overload, this method signature, and you're going to get a null pointer exception, which is not what you meant. Because it's a bottom type, it resolves to any ref. In implicit search, there's an overload available that takes a reference type. Implicit search is simply not going to happen. So you can add your implicit, but it's never going to come into effect in the language. The way to work around this is, and similar issues by the way, is to add a method overload. And this method overload operates on values of null, but it should only apply when your type t is a reference type. The way we encode it in Scala is, we have our entry point, we have all the stuff that we already put in there, and we add a should be method that takes, some random value that we don't care about of type null. Now, type null in Scala has only one value, and that's null. So whenever someone says whatever it is should be null, it by definition resolves to this method overload. And we also require evidence from the compiler that our type t, because this implicit class operates over any t, which could be a value type, we want to constrain this method to only be available for types that are reference types, and that's the evidence we ask the compiler to provide. Next up, parameterization. So there's something really odd going on with PowerPoint today. Hold on a sec, I'll try to, yeah. Okay, so we have certain predicates that are parameterized. Okay, things like equal to, or starts with, or whatever. They take parameters. So we would like to have this expression 3 times 4 should be equal to 12. The equality predicate is actually really, really easy to implement. Okay, you have a def equal to over some type t, it takes the right-hand side, and the test is simply to check the equality of the value we're given to the right-hand side, and the failure message is whatever value we got is not equal to right-hand side. Okay, so that's trivial. The problem is, we just broke one of our earlier rules. Okay, this expression above, 3 times 4 should be equal to 12, has 4 parts, has an even number of parts. And as we said before, you can't really get it to compile. So, to work around this, there's unfortunately only one way I'm familiar with, and that's to add parentheses. And once again, this really seems to be not working right. Okay, so if you've worked with ScalaTest or Specs², or really any DSL, and you kept wondering why you have to put parentheses in weird places, like after B, or in certain other use cases, this is why. Okay, and there's no way that I'm familiar with to work around this limitation. So what this means to you, the domain-specific language designer, is that the language you're hosting in actually limits what you can do in your domain-specific language. It adds constraints on your language. So suck it up and add parentheses, because that's what you got to do. Another issue you're liable to run into is grammar variance. Okay, we have a set of new assumptions here, things like start with, end with, contain, match, regular expression, etc., and some example sentences. And there's a fundamental difference between this version, or rather, this shape of assertions to our previous shape. Any ideas? Yeah?
It depends on the type on what you're trying to check.
It depends on the type. Everything depends on the type. Like, you have a piece of data, it's typed. Some assumptions only apply to some types. That's not the difference. The difference is actually really, really, really trivial. There's no B. Okay, we have ScalaIO should start with Scala. There is no B. Earlier on, we had should be. Now we don't have it. So why this ends up being something of an issue is that really for our domain language, we have several. In this example, we have 2 families of predicates. Okay, and in linguistic terms, we have simple modal forms of the type, list 1 to 3 should contain 2. And we have the other shape that's called compound subjunctive form. Don't ask me why. I did Wikipedia searches and came up with this. And it's anything should be equal to 12. Now, your domain-specific language is aimed to be readable. And in this case, it's aimed to look kind of like English, or at least common sense, almost English-like expressions. So we need another verb, right? We need to add support for should alongside should be. A simple solution for this would be to just take our entry point and add, split off the code that actually does the test and just add the verb. Okay, we have should, takes a predicate, we have should be, takes a predicate. This is very bad. And the reason this is bad is because it allows you users to have illegal expressions or illegal grammar in their usage site. So, for instance, in this case, list 1 to 3 should be contained 2. Okay, pretty much anyone who has any grasp of English will look at this and start cursing, basically, okay, because this is crappy English. But there's nothing encoded in our domain language that makes this impossible to do. So what we lack is, we lack an ability to differentiate between these two families of predicates. The way we solve this is, first of all, we need some way to differentiate between them at the type level. Okay, so we add two traits. One is called a modal predicate, the other is called a compound predicate, that derive from our earlier predicate structure. Next, we modify the verbs so that should only takes modal predicates and should be only takes compound predicates. In order to enforce this decision, okay, because up until this point we had just, anyone can take a predicate, derive from it, and that's that, we want our users to have to pick. Okay, when someone defines an assumption, defines a new type of assumption, you want to force them to make a conscious choice about whether that fits in the should be pattern or the should pattern. The way you do this is pretty simple. You make the base trait sealed, you take all of your, you take that base trait and the different families of traits you have, shunt them off into a separate compilation unit. From that point on, your users cannot directly inherit from predicate of T, they have to pick and choose. And obviously we need to modify our existing predicates to subscribe to one of these two families. The final issue I'm going to cover is around negation, and that's actually that actually happens to be a pretty hard one to get right. So negation is a modifier on the verb. Okay, what we want to say is a list should not contain something. A string should not be starting with something. Okay, it's a modifier on top of our existing syntax. But it's not just syntax. In order to actually negate any type of assumption, we need to have two things in place. We need to have the ability to negate the predicate, or rather to invert the test that the predicate actually offers to the framework. And we need to have, because our messages are in English and we don't want to have a whole language infrastructure in place to invert the messages, the failure messages, we also need to ask our implementers, extenders, or ourselves as language designers, we need to require also a negative failure message. Okay, so if a list should contain some element, our error would be, this list does not contain the element 2. Whereas if our assumption is the list should not contain the element 2, our error message becomes inverted to something along the lines of this list does contain the element of 2. Or this list should not contain the element, but it does. Right? So the failure message needs to be provided by the predicate. So we need to extend the programmatic model that we already have to support this. But the first thing we need to do actually is decide what it's going to look like in terms of grammar. So for compound predicates, such as empty, we have several options. Probably more than 3, but these are sensible 3 options. One thing we can do is we can add a should not be verb. Okay, simple enough. Another thing we can do is to add a not modifier that is a function that takes a predicate and negates that predicate. And then we have the should be in place, should be not empty. It's a bit awkward in terms of English, but there are reasons to do it like this, as I'll show you. A third option would be, we have this list and it should not be empty. For modal predicates, we have two similar options. Programmers should not start with Java, hopefully. The other option is programmers should not start with Java. Okay, so these look very similar. You can argue forever about which option is preferable, which option is more readable, etc., etc. But you need to make a choice because the mechanics underlying each option are vastly different. The implementation details are different. So you really need to make a choice before you go into the implementation details. And this is an aesthetic choice. There is no right answer. Okay? You just need to pick and choose. And in this case, to give an example, I picked these two options, which is rather, I opted to give a not function that acts as a modifier on existing predicates. And the way this is implemented is as follows. Here it gets a bit messy. The first thing we need to do is we need to take our trait, which is now sealed, that's called predicate. We need to add a negation or negative message, negative failure message to that predicate. And we want to have some sort of API that the predicate provides to give you a negative version of itself. And this is a bit messy because we have several types of predicates, and our verbs expect families of predicates. Okay, we can't do this in a generic way without some type wrangling. So we can't just return a predicate of t, because our should be and our should verbs expect subclasses of predicate. They're not going to work. What we need to do is we need to require each predicate family to provide a self type or a return type. So that's a type member called self. It takes type parameter t. It derives from a predicate of t. It's a bit messy syntax, but you only need to do this once. Or rather, you need to do this once per predicate family, which in our case just means changing a few lines in two traits. It's not that big a deal. So the negate API returns a value of that self-type parameter. We need to add these features to each predicate family. So in our case, what we have is, to exemplify this, we have the modal predicate, okay, and the self-type for that is modal predicate. Okay, we expect if we have, say, contains, the negation of contains would be also a modal predicate, so it can be fed to the should verb. And then we have an implementation of negate that just returns a new modal predicate. It takes the original test and applies an additional function to its test to invert the result. We take the failure message and instead of returning the original one, we return the negative message. In case for some reason someone wants to negate us multiple times, we just basically switch the negative and positive failure messages in our return value, and we're done. This applies to any modal predicate. And we need to do a very, very similar change to compound predicates. Finally, we need to add the actual API that allows us to modify sentences. So that's the not function. And the not function operates over some type t. It takes a predicate of that type, and it returns this is something I learned from John Pretty a while ago. It returns a dependent method type, I think. Right, it returns a dependent method type that's the type member of that predicate. And the reason this looks a bit wonky, but the reason we don't care is that the compiler will end up doing all the resolution for us, so it amounts to being correct, as you'll see. Okay, what this basically does is it takes a predicate, it negates it, and it spits it out. And that's it, and it works. Okay, because list should be not empty. Empty is a compound predicate. The return type is embedded in the compound predicate trait is a compound predicate. So that can be applied to should be. And it's the same thing with a modal predicate. Okay, so this thing works over all families of predicates with just the one function. In terms of techniques and stuff you might run into to extend your API or your domain-specific language, this is what I have for you today. The next thing, obviously, is to make a whole bunch of money off of your domain-specific language. Good luck with that. And in terms of content I have, I'm done. If you want to see the sample code, there's a GitHub link up there that has all the code, and I think we have time for questions, so if anyone has them. Yeah?
I work quite a lot with RDF, resource descriptive framework, and they're all, everything's triple there. Noun, predicate, object, subject, predicate, object. And working with some of this, it strikes me that RDF is sort of a super language for expressing virtually all of these things. Is that something you've looked into or considered or know about? Or?
So, just to repeat for the camera and the audience in the back, the question was, it would appear that RDF, being a kind of language that's based on triplets, might be a good framework for expressing a lot of these things. It probably is. I haven't really done any serious thinking on that. I would say that the language itself, though, is very, very strict. Like, you can't really take it and apply to many different domains in a way that ends up being comfortable for the user, at least as far as I can see. Yeah, it might be, I'd love to see an example of that, but offhand it doesn't
Maybe
appear.
afterwards, yeah.
Pardon?
Maybe afterwards.
Gladly. Any other questions? Yeah?
The type parameter for the predicate was contravariant.
Yeah, contrary.
Why is that?
So the question was, why is the type parameter for the predicate contravariant? And the reason is that a predicate consumes data. It takes in a value. And a predicate over some supertype also applies to the subtype. So if, for instance, you have, you have a gent-reversible once, okay, and you have an assumption on that, such as empty. That applies to anything that is a gent-reversible once. Okay, you only need to define the empty assumption once for the topmost type where it makes sense, and then it applies to sequences, it applies to lists, it applies to sets, to just about anything, to options. Actually, options need some wonky implicit conversions, but anyway, it almost applies to options as well. So that's why. Any other questions? Okay, if you have any questions down the road, or need any advice or assistance with your DSLs, I've only covered a very small subset of the tips, techniques, tricks that you can do with Scala to generate your DSLs, but I'll be very much happy to help where I can, and thank you for your time.